That's the basic motivation behind methods that try to reduce dimensionality. Now, why is dimensionality a problem in practice? Most of the data sets that you will be dealing with will be high dimensional. So images are high dimensional, speech is high dimensional, text is extremely high dimensional. That high dimensionality, however, is apparent. It's not actual. What I mean by that is we only get 1 million dimensions in text because we choose to represent text with individual words. We choose to associate each word with a separate attribute. That's what makes it high dimensional. When we're working with images, so bitmaps, we're choosing to make each pixel a separate attribute, and that's how you get lots and lots of dimensions. And really what's happening a lot of the time is the data underneath, it doesn't uniformly fill that high-dimensional space. It lies on a low-dimensional subsurface within the space. So here's an example of what this might look like in 2D, right? So the data points here are 2D, and they don't lie on a line, right? But it's possible that the data points are hugging a one-dimensional structure. And any deviation from that structure is just noise. Right? So the signal is really where the point is along that red one-dimensional structure. And any distance between the red line and the point itself is just accidental. That's just noise in your observation. That's a Swahili guy measuring a different height than a British guy. Right? It's very good to illustrate this with handwritten digits. So with digits, suppose that my digits are 20 by 20 bitmaps, and I'm just using black and white. So the apparent dimensionality of that space, what you get as input, it's 400 dimensional, right? Because you have 400 pixels, and each of them is binary. Now, the thing that you want to realize is, yes, these bitmaps really live in that space, but they don't fill that space. They occupy a really, really tiny corner somewhere in that space. And the rest of the space is filled with things that are not digits at all. So if you imagine that space and you try to draw random samples, right? What are random examples of that space, of the space of digits? What you're going to get, things like that, right? That's a typical example from that space. That's a random 20 by 20 binary bitmap, and there's another one, and there's another one. And you could sit here all day iterating through random examples of that 400-dimensional space, and you wouldn't see a digit at all. Right? The digits, they also live in that space, but they're extremely rare. They take up a tiny, tiny, tiny fraction of that space. And really, the true variation, the true dimensionality of digits should be a lot smaller than 400, because digits are constrained. I cannot... the reason that is not a digit is because you get random pixels on and off. And digits are constrained. You put pen down on paper and you move it. So it has to obey laws of physics. My pen cannot move erratically. I'm not a plotter, right? It has to move in a smooth shape. So the space of digits is really sort of how many variations of the pen stroke you can have. It shouldn't be the number of pixels in the rendering.